Hello everyone, welcome to Finite Element Method tutorial. Today we are going to use Abaqus to solve a lap joint of a sealed pressure vessel problem. So here is our problem statement. We have a pressure vessel which has the upper half and the lower half. This L shape represents the pressure vessel and part of the pressure vessel, and this is the lap joint for the pressure vessel. The dimension is listed here, and you also have a slot for sealing. And for the sealing, you will have an O-ring with 0.25 as the diameter, and will be placed inside the slot. And the bolt is added here with a diameter of 0.5 inches. And the bolt, we use a real geometry. Notice that we can actually use a beam element to represent that, but here we just use the real geometry to show you how to add a constraint. And here is a top view of the pressure vessel. So the pressure vessel is has a diameter of 24 inches, and the thickness is 0.2 inches here. And it was jointed by 15 bolts. Since the geometry is cyclic symmetric, we will only simulate half of the bolt. So 15 bolts, each of them take 360 over 15 degrees, which is 24 degrees. And we only simulate half of that, so our simulation angle is 12 degrees. Here is some useful reference point for you to easier create the model. And we'll show you how to do the CAD part later in Abaqus operating thing. So here's a material property. For everything other than the O-ring, we use a steel, has a Young's modular of 30 megapsi, and the Poisson's ratio is 0.3. Alpha, which is the thermal expansion coefficient, is 8 microinches per inches R. And the rubber, we use hyperelastic material, Moulin rivaling model for that, with a material property of C10 equals to 43.5, C1 and D1 related to the box modulus, which is pretty low. That means it's nearly incompressible. And thermal expansion here. Notice that these constants usually should be determined in experiment. So here we just select the commonly used materials property sets. For the contact, steel to steel, we have a friction coefficient 0.2, and steel to rubber, we have 0.35 as a friction coefficient. And here is the step we're going to apply. In the initial part, we have cyclic symmetric condition. And also we have a vertical displacement constraint to prevent the pressure vessel moving up and down. And the contact, definitely geometric contact inside the entire geometry. And for step 1, we apply the preload inside the bolt, and also we use a press feed for the O-ring, which can be found in Abaqus. And for step 2, we are going to apply the internal pressure. However, this is only part of the thin wall pressure. It's not closed, so we cannot actually simulate the longitudinal stress. So we manually add the longitudinal stress to it with, according to thin wall pressure theory, it should be equal to PR over 2T, so it's 15,000 PSI. And for step 3, we're going to explore how the temperature change affect the entire geometry. We apply the temperature change of 150 Fahrenheit, and see how the geometry will change and how the stress will change. And let's see how do we apply Abaqus here. So I just stepping toward this for you, geometry for you to better see the geometry. First, we're going to create a part, let's call it upper half, with a 3D deformable solid, but we use revolution here. So approximate size we enter, because the diameter is 24, so we probably enter 30 here. Notice that we need to draw the half of that. So we just enter those points here. So 12, 0, 12, 3, 12 point, sorry, 12.2, 3.2, 0.3, 14.2, 0.3, 14.20, 12.950, 12.95, 0.1, 12.45, 0.1, 12.450. And the last one is for the bolt, so it's 13.40. And then it's pretty simple. We just simply connect all the geometry and you done the CAD part. Notice that you can also draw this point on the top surface. This for cutting the hole later. Finish, then click done. This angle should be 12 degrees. You will have the geometry like this. But it doesn't have the bolt hole here. So the bolt hole is diameter 0.5. So we're going to draw a semicircle and do the cut extrude here. Vertical on the right, which is this line. And draw a semicircle for that with the diameter 0.5, so radius 0.25 from the center of the bolt. Pointing up and then through all, you will have the hole. Since the geometry is symmetric, so for the lower half, we can simply copy this upper half and call it lower half and do a mirror part with XZ plane. So you should have the lower half now. Now let's draw the O-ring. Let's draw the bolt first. So 3D revolution, and this is just do 2 probably. So again, we enter those points 0.250, 0.25, 0.3, 0.35, 0.3, 0.35, 0.38, 0.3, 0.38, 0.3, 0.53, 0.53. You should have all the geometry here. And we only draw half of the geometry, and then we can rotate 180 degrees because we are doing only half of the bolt. So to do that, we can do this one, mirror. So we mirror the, first we select copy because we are going to copy this one. And oh, I forgot to create a mirror line. So create a constraint line first. So 0, 0 to this one. And we can probably create another point, it's called 0, 0. So now we can do mirror, copy, and select this line as the mirror line, and select the entire this points. Now you can have the whole geometry point, and then just simply connect them together. And select this line as rotation line, center line, and the revolution we want it to be rotating the other way, like counterclockwise of XZ plane. So we will revolve the direction. So, sorry, I forgot to change the angle. So go back to bolt feature, this one added, and this angle, we should be 180 degrees. So you should have this geometry here. Finally, we need to create the O-ring. Again, we use revolution, and then O-ring, we just need to enter this center point, which is 12.70. Sorry, we can do this 12.70 first. And then, sorry, I make it too small, but it's fine. Now we do the dimensions. Diameter 0.25, so this one we can do 0.125 here. This is the radius. And click down. Angle, again, we should rotate 12 degrees. Now you should have all the part, which is upper half, lower half. Let's see the XY plane. So upper half, lower half, O-ring, and bolts. Now material property. From material property, let's go back. We have two material, which is steel and rubber. So create the material here, which is steel. General elastic, and Young's modulus 30 MSI, so 30 E6. Poisson's ratio 0.3. And now we need thermal expansion coefficient of AE minus 6. And for rubber, we use elastic, but we use the hyperelastic material. So we choose the Monning rivaling material, which means the strain energy function is Monning rivaling type, and we choose coefficients. And is 43.5 and 8.7. 43.5 and 8.7. And the Poisson's ratio 0.001. And again, we need a thermal expansion coefficient, which is 4.2 E minus 5. Okay. Then we create section. Steel sect. Rubber sect. Now we assign the section. For the bolt, we assign we don't need to create set here. So we assign the steel. For lower half, we assign the steel. Upper half also steel. For O-ring, we assign the rubber. Now we go to assembly. I personally like independent. So we draw those things. You can see the bolt is not with the whole geometry. The geometry, you should have a little bit overlap here. And later we're going to apply press feed to get rid of the overlap, and it will become your stress. So we need to do a constraint to move the bolt there. We use this line constraint. So this edge should be aligned with this edge. They should point at the same direction. So, okay. And also, see, it's a little bit rotate here. So we also need this line to be aligned with this line. Oh, sorry, I forgot to click. So we select this line, constraint with this line, and they should be in the same direction. Click OK. Now the bolt is on the correct location. Before we actually go to other step, we need to do some partition of the geometry. Because for example, this geometry is weird it's hard to be meshed. So we wanted to be more close to square geometry. What we are going to do is we are going to create some datum plane from point and normal first. Point and normal. So first we want to cut the upper half on this point. You can see we have a vertical datum plane here. And also this point, we select all the point that can have vertical cuts. And also this point. Oh, for the bolts, we don't actually need it. So we just directly go to this point. And now we create partition of surface. We cannot directly partition the cell using the datum plane because this is a revolved geometry. This is not a parallel geometry. Create datum plane, select this cell, enter, select this datum plane, this cell, and this two cell, this two surface. Go back, select this one. This is a little bit hard to see, so you need to be patient about this step. Sorry, this one. Select this surface and select again this two with this surface, this two with this surface. Now you can see that all this surface is partitioning to different part. Now we need to partition the entire cell with this lines, but with a revolve type. So we use this one. Use the partition the cell using the swap edge. So we can partition the cell with this edge, choose swap along edge. Same things apply to all the line with any this revolution edge. We just speed up our participation. Although this step takes time, but it's worth to do it because it will make your mesh much better. Oh, sorry, I forgot to select the edge. Any age is okay. For example, this age is also okay. When you finish, you should guess the geometry look like that. This is vertical control. So now we hide all those data plane by selecting that and then use this button. Now it's hide, you won't see it. So now we need to create like horizontal participation on the bolt. So we directly do this one. Partition using using plane cut. So we are going to partition our bolt in the middle first. This one, this middle cut is going to apply the preload and select this vertical line, and the bolt will be cut in the middle. So upper half, point and normal, cut this one, this, also this one, point and normal, cut here, this one. So you should have 1, 2, 3, 3 part for the upper half. Also symmetrically, you should have 3 part for the bottom half. Okay, so our partition of the cell is done. To confirm that our mesh is okay, we go to mesh first. You can see 2 orange here. So we are going to change a control for these 2 cells. Instead, we use the hex domain partition and use the swap here. Make sure all your geometry is either yellow or green. And mostly it should be green and it will look better. Now we assign global seed to only the upper and lower half. So we do 0.2 here. 0.2 for the global size, but for the global size of the bolt, we do only half of it, so 0.1 here. And for this one, we are going for the O-ring, we are going to make it very fine, 0.05. Now we can mesh. You will have this warning, but it's fine. You can see that here, now it looks a little bit too coarse. So I'm going to remesh it. Top and bottom, the seed, 0.2 is too large. Think about that. You will have only one element through the thickness because your thickness is 0.2. So probably we are going to do a 0.1 here. And then as I mentioned previously, your mesh for the bolts will also change to half of it, 0.05. And for the O-ring, it will be even finer. Do 0.025. Now we can do the mesh. It looks much better now. You should have at least 2 elements inside the thickness direction. And then your mesh of the O-ring should be fine enough, and everything should look pretty organized. And after your mesh is done, don't leave your mesh first. We need to select the bottom surface to apply the boundary condition. I will explain why later. So to apply the boundary condition, to select the set, we create a set called like bottom constraint and select the node. And we select the biangle first and click here, you will select the entire surface. But now we change it to by feature edge and hold control and unselect this edge and this edge. You can see that we select all the nodes except on the edge. I will explain why we need to do that later. Now since everything is fine, we can create our step. Remember that we have 3 steps in our problem statement. First step is related to preload, and second step is the internal pressure, and third step is a temperature change. So we create the first step is like a press, feed, and preload static. And since we need some time to convergence, we can make it smaller. If it is not enough for conversion, you can make the initial even smaller. But then your increment must be large enough because it's going to take a while. It's going to take time. And your minimum, make it 1e minus 15 for general convergence test. And we turn on the nonlinear because the deformation, especially for the O range, is large. And create the second step is the inner or thin wall pressure. Same things apply here, 1e minus 5 and here 1e minus 15. Make it a little bit larger to make sure it's converging. And finally is thermal effect. And 1e minus 5, 1e minus 15, 300. Sorry, 300 is enough. Normally even 100 is enough. Just want to guarantee that it is converging. So now we can move to interaction. For interaction, we need to do some trips. We need to create some surface first so that it's easier to see to be assigned later. So go to your tour surface manager here. Now we can create some surface. Before creating that, probably it's better to select the instant and hide the unrelated instant. Select only the top and show only the top. And create like, first is contact between the top and bottom. So we call it top bot. And here we select by angle and this surface and this surface. Second one is top washer. Top washer is going to be, let's select individual, only this surface, because your washer is going to be something around the bolt. And create, then it's the entire structure with the bolt. We call it structure bolt. because we only can select the top surface now, we just select that. We'll modify that later. And finally is the structure to O-ring. Similarly, we can only select the upper half now. So we just select the upper half, hold shift to select all of that, and then down. Now we use this one to go back and select only the bottom half. First, we create bolt top for the contact between bottom and top. Change it to biangle. Hold shift. And we are going to create a butt washer, which should be this surface. So we only select this part. Now we need to modify the structure to bolt. Select edit and hold shift. Remember to hold shift and select this surface. And also structure to O-ring. Edit and hold shift. This one, and also this one. And to double check, we select the top and bottom together. And double check the structure to O-ring should be the entire block, all the surface inside the block. And top and bottom should be this one. And bottom to top should be the same thing. Bottom to washer should be this surface. Top to washer should be this surface. And the structure to bolt should be the cylinder area. And everything is fine. Now we create the things related to bolt and O-ring. So we select the bolt. Bolt to top, which should be this surface. Bolt to bottom, which should be this surface. Finally, bolt itself, which should be this two surface. And this is done. Now we go back and select the O-ring. For the O-ring, create O-ring for this surface. Now we can create a contact property. Go back and select steel to steel contact. As we mentioned before, it should be 0.2 friction coefficient. And for normal behavior, we just select hard contact, allow separation after contact. That's very important. Okay. And then steel to rubber. This is 0.35. And also normal behavior hard contact. Now we can assign the contact. First is top and bottom contact. In the initial, select the surface to surface contact. And master surface, because we are going to apply load on the top, so we select the top to bottom. And the slave is bottom to top. And steel to steel. Also, we need the top and washer. We select the top to washer as the master, and slave we select the washer bolt to top. So it should be here, bolt top. And use steel bottom to washer. And bolt to bottom. Steel. This is a structure to bolt. Top will be structure bolt. Sorry, master will be structure bolt, and slave is the bolt. Finally is the structure O-ring. We select the structure O-ring here, and then slave we select the O-ring. Steel rubber. So in total, you should have 1, 2, 3, 4, 5 contact. And then we can go to the load. We finish all the initial here. Definitely, some of you may know that we can assign a cyclic symmetric in the in the contact part, cyclic symmetric, but it cannot be applied here since we are going to apply the preload later. So a better way is to assign a local symmetricity. So that is what we are going to do now. So for symmetry, first we need to create the datum plane. Let's call it front surf. And this is our front surf. We choose this to be origin, x pointing to this direction, 1 pointing upward. So you can see the symmetric axis should be z-axis of this coordinate system. We choose another back surf, which should be located at the bottom, at the back of the geometry. So select this as the thing, and let's do x is pointing this way, and y is pointing upward. So your z is the symmetric axis, and also the normal axis of this surface. And now we can create symmetry in the initial front scene. Move to the front surface again. Symmetry. Now we need to choose all the region. Here. And use Z, but we need to pick this local coordinate system. So it will be symmetry to the local Z direction. Similarly, we are going to apply back seam here. Select all the surface you have and select this symmetry axis we just have and use Z symmetry. Now you can see that why we don't assign any, we need to choose the set here. This 2H is already have some boundary condition. It cannot be overdefined. That's why we need to choose the node that is not lie on this 2H. Now finally, we apply the vertical displacement constraint. So here, create the Y constraint and use displacement and select the set we just create and choose U2. And you should see that you have a lot of constraint Y displacement here to prevent the structure from moving up and down. And now we can assign the step loading. First step, we have a preload of 7. Usually preload inside the bolt is 14 kips. But right now we are only simulating half of the bolt, so it should be 7 kips. Inside load, create preload and choose your first step. And here you will have the bolt load. And select the interior surface and select the surface we just created in the section. And done, you can choose whatever, for example, purple, and then magnitude enter 7 E3, 7 kips, so 7 E3 pumps. And so you should see two angles here. Sorry, two arrows here to represent the preload. And then is the press feed. Go back to interaction. Here in your O-ring interaction, in the second step, we added that. And here you select the interference feed. And select this one, gradually remove the slave over during the step. So if you have a press feed on the slave surface. And give you also give you a, it should show modify here. It also will give you a force. And your first step is done. Now it's your second step. You should have internal pressure and longitudinal stress. Internal pressure is easy. Here, create internal pressure, but on your step 2. Pressure. Oh, sorry, not bolt load, but pressure here. So this surface and this surface is your inner wall. And the magnitude is 50 psi. You should have like arrow pointing inside. Now apply longitudinal stress. We only apply on the top surface, and the bottom surface should have corresponding reaction force. So create the longitudinal stress. We use pressure for that so that it's easier to apply. So pressure should be 1500, but 1500 is in tension, so we enter minus 1500 here. So it should be in tension now. One thing I forgot to mention is here is nonlinear, it's very important. So then your stress will follow the geometry to rotate. And make sure that all of that is nonlinear is on. And then the third step is apply the 150 Fahrenheit temperature change. We use this predefined field here. Let's call it temperature field. So it should be in your third step, temperature, and select entire geometry to apply the 150 Fahrenheit temperature to that. Now that everything is done, check again your mesh and your properties, then we can create a job here. Let's call it thin wall or lap joint. So since my computer has 12 logical processor, I can enter a maximum of 12 here by just leave 2 of that for other work. So I do 10 and use GPU computing. And then we can submit the job. Can do data check first. This should report. The data check is complete successfully, so you can submit now. I already run the analysis with the same settings, so this analysis is going to take some time, so I'm not going to run it here. But general question for the fail of analysis, including like if your step is not fine enough and your initial step is not small enough, it can report some error. And also if the geometry like is not converging, it says something like too many attempts. That means that can be related to your mesh size. Try to finer your mesh, especially the contact part. And if you do everything correctly and the analysis runs through smoothly, you should have the result. I'll show you the result here. So let me select my result. Here. So this is the result I have. You can see that I have actually 4 elements inside the thickness direction. That means my mesh is like 2 times finer than what I have, what we say in the tutorial. If finer the mesh, if your geometry is not convergent, always try to finer your mesh first. And let's see how the displacement played a role here. So we select U2, and you can see that at first it's not the overlap is not removed, so you only have a preload here, and this play acting as a cantilever beam. So those 2 geometry will split, one going up, one going down. While you keep increasing, this overlap is removed here. So it's trying to reply by a stress. If you see the stress, you can see the stress concentration here. And it has the largest displacement, so you won't see those displacement. This is the largest one. And this is the end of the first step, which is the press feed and preload. If you see stress, you will see stress concentration on the corner. And if you see, for example, shear stress here, also all the stresses, the corner of the bolt should have the largest. Other than the tension here, this is the tension. You have the tension here and compression for your geometry at the washer because of the preload inside the bolt. Now, if you have keep increasing the step, now is the internal pressure here. With the internal pressure applied, because of the longitudinal force, you can see a split inside the geometry because of the longitudinal force. This will also change your magnitude of displacement. The top is moving up a little bit so that this contact is not as large as previously. Now, if you keep going, now apply the thermal, you can see the thermal expansion of the geometry. See, the geometry is moving to the right and your maximum displacement is applied here. This entire O-ring is expanded also. To see the full structure, first we can get rid of the mesh first. And then let's see how the O-ring is doing here. So we select the instant. We hide these two instants, only see the bolt and the O-ring. What we are going to do is we can go here and choose this ODB plot thing and choose this mirror and partition. So mirror the display body and mirror by the axis of from surface first. By applying and mirror axis, remember our normal axis is Z, so we select the XY plane. So you can have the full bolt and the part of the O-ring. And we duplicate that by 15 times because we have 15 bolts. Now we can see sorry, I choose the wrong axis. Our axis should be Y-axis. Now you can see the entire O-ring and the 15 bolts here. So we focus on the stress here. All 15 O-ring have, all 15 bolts have some initial preload at the very beginning, and with the increasing in geometry, the O-ring expand a little bit, not too much. If you see the displacement, it should be even clear, more clear. Let's choose the U3 here. You can see the expand of the O-ring. And if you want to see the entire geometry, we can see this is the entire geometry. So it has simulate part of your seam wall pressure, and 15 bolts is joining that. Inside the geometry, you will have the O-ring. And this is how to apply Abaqus simulation of seam wall pressure lap joint with O-ring for sealed. I hope that you can learn something into